loading, and then there's some kind of connections on the end. What's the first thing you do?
Find the reaction.
Find reactions at the supports. Now it could be, and I don't remember if I actually gave you the reactions at the supports. I might give you the values just so I can test you on the shear and bending moment diagram. But if I don't give it to you, then you have to find that. What's the next thing you do?
Set up your diagram.
Right. You draw vertical lines down the loading. You make a shear, put a 0, a plus, a minus, and put the units. Draw another horizontal line. Give yourself enough room. Use the whole page moment and put the units. Be careful. Make sure you put the units. You know that you start at 0 and you end at 0. That's the way to check. And then we're going to look at if you like to have this, you can put this on your cheat sheet, the thing that Ben made up. Right? So if your forces go up, your shear goes up. Forces go down, shear goes down. Distributed load goes down, then you have a diagonal going down with a negative slope. Okay? If you have a I'm not going to give you any triangulars. No triangular loading. There are a few problems with triangular loading in the homework, but I'm not going to give you triangular. So we're only concentrating on the top. So if you have point loads, you know you're going to get rectangular, either positive area or negative area. If you have distributed loads, you know the slope is going to go down. If you have a slope going down but a positive area, you're going to get a parabola going up. If you have a slope going down, you have a negative area, you're going to have a slope going down. I mean a parabola going down. Why? Let me explain that. There's more material here. Right? There's a lot more material. There's a lot more change happening here than here. So there's a bigger change here than here. Here, the bigger change is here. It just drops off. I mean, that's non-mathematical way of describing it. Okay. So once So first you're going to find the reactions of the supports. Do you remember what I said to do before you draw these lines? Or draw, let's say second step is to draw the diagram, draw the lines. And I want them drawn down from the loading, and you have to divide it up into sections depending on what the loading is. But everything that's in here, you're going to communicate in shear. But what if there's something special here? What's the special thing that you have to do down here?
Moments.
Right. So if there's a concentrated moment and you see it, make sure you come down and put a little dot or something here to remind yourself that you're going to need to look back up at the top. Because when you draw the shear diagram, you're only looking here. When you draw the moment diagram, you're only looking here except for that spot. So to put a dot here to remind yourself. Yeah.
And for the concentrated moment, you draw it on the diagram opposite of what's given?
So if I have a positive moment, I draw it go down. Can you guys see? I might have to stand up. So if it's a positive moment, you go down. Now, somebody asked me, do you need to show all the math? Remember how I took the beam and I put a V and a shear and did X and did all. You do not have to show me this. But if you want me to give you partial credit, I need to see something. So if this goes up and then it comes down, and this is area 1, why don't you write area 1 equals base times height equals 5 times 2 equals 10. So I know when you go up 10, I know how you got that number. Right? If this goes down like this, I'm going to need to know what this distance is. So you could say y is equal to mx plus b, y is equal to whatever m is, x plus whatever b happens to be, and then when Does everybody know what I'm doing? When y is equal to 0, then x is equal to what? Show me how you're doing the math. Like this one is going to be a positive area down, it's going to go up like this. Well, how did you know it went up to 5? Because this area of 2 is equal. Show me some math so that if it's wrong, I could at least see if you made a math mistake. If you did 5 times 2 and you got 8, and you just put a number here, and I don't know how you got the 8, I'm just going to take off for that whole section. But remember, what does it need to do at the end? They need to close at 0. So that is your check. If it doesn't close at 0, you made a mistake and you have to go back and find it. Also, I could ask you, like at the end of all our shear and bending moment diagrams, a question I asked you is what is the maximum shear and what is the maximum bending moment? Right? And how do you find that? If this is up to 10 and it's down to 20, what's your maximum shear? 20. It's the maximum magnitude of the value. Good? Questions on shear and bending moment? Okay, so let's go to friction then. And aside from my email highlights, I mean, you really learn friction looking at the videos or on your own. So what's the main thing in friction? What are some key things? Oh, you didn't talk. I want you to talk first. Talk for 5 minutes about friction.
Then you have
Shear+Bending movement. You might have to solve the both. If you're tipping, there's no normal at the centroid. It's at the point.
So yeah, just looked up to the table.
don't worry, yours is not.
What was the condition where you knew that it was gonna slide?
Well, yeah, we just we have our little friction.
Whichever is us, we have sliding and tipping. Okay, so we'd have to check for both, I guess.
Well, but also
The
she
one
was
where we have
emphasizing
the
Yeah, one for tipping, one for
value.
sliding.
by itself.
Yeah,
I'm saying if he is too, like 2,500, this one would be bad.
yeah, because you're using less force.
Like if there's tipping happening, we're not gonna have
Most of the time.
Yeah, so you solve the
yeah, you're gonna testing or whatever, so then that goes away, yeah, so you're gonna find a different value. If you have previous
Yeah, most of these problems include like having to solve for the heat regardless of what the question is.
Every time I think about it, I still remember like being in Marcus's class and somebody drew a picture of
It's really gnarly.
like
Find
sliding,
the, find
sit
out
on it,
You
why, of course.
Yeah, it's just you just have to put in a bunch of variables, but then it's simultaneously tipping and sliding. So see how you get individually actually
it's not sleeping, but that would be a waste of time.
Yeah, that's mostly what I remember.
It'd be wasting
Sliding
your
or
time.
tipping. And then mu would be unknown. And then you take summation. Was it mu times the normal? Is the
You gotta put one here.
Oh yeah, so there's like static and there's kinetic.
It's like your plastic version.
So the max static.
It's better than the big that I was getting. It actually like stops being able to.
Okay, can I get everyone? Okay. So I'm looking at the friction chapter. Right, it starts on page 379. Starts on page 379, and then there are some example problems, 1, 2, 3, 4, 5, 6 example problems, and then it goes from problem 1 to problem 61. If you look at the homeworks, I don't think I asked you for a homework after 61, friction, no. So I asked you for problems for friction, you had problems 5, 17, 21, 27, 37. So these are the ones. So remember, I'm always picking problems from the textbook, right? So make sure that you look over the example problems, and then you don't have to go any further than 37. This is 37. So if I were you, I mean, friction problems, they all have a little twist to it. I would go through, read each one, and figure out how you would approach each one. Go through all of these. Go up to number 37, and then that's it. You don't have to look at any more in the book. I'm going to choose somewhere between 1 and 37. Okay, so I'm narrowing it down. Do a lot of friction problems. Okay, so what's key on friction?
Mu.
Mu. So now we introduce mu, which allows us to do what?
Friction equation.
Find the friction equation, or know the friction equation. So in this case now, we have one extra equation. And you notice that all of these are 2D problems, right? So typically on a 2D problem, how many equations do you typically have? 3 equations, right? Some of the forces in the x equals 0, some of the forces in the y equals 0, and some of the moments in the z equals 0. Well now, because it's a friction problem, we have one more equation. So now you have a total of 4 equations, which means how many unknowns can you find?
4.
You can find 4 unknowns. So that's the big thing about friction. How do you know which way the frictional force goes? Opposite the direction. So if the block, the example I did on the video, I had a block on an inclined plane and it was held by a rope. If the rope was high, was a large number, the block could slide up. If the rope was cut and it's low, it could slide down. So the important thing to know is in that particular option, there were 2 ways you had to analyze it. I'm hoping you guys watched the video. So you analyzed it and found what the force was for P if it slid down or for it to go up. Okay? And the force P, since we're using all equilibrium equations, meaning there's no motion, the value of P that you get is for still static equilibrium. So for that block, there was a range of values that rope could have that still keeps that block in static equilibrium, not moving. It was only, I don't remember what, 134 to, I don't remember what the numbers were. Matt, question?
And that, our new equation for friction, that would be our maximum friction force. That, because I was watching the videos. There's 2 different friction values. One of which you can find in, like, let's say that force is in the x or the y, and then you have that friction. Right. So and sometimes they're different, and that's.
So you're talking about when it's sliding or tipping, or do you mean with the block?
Yeah. I guess when it's sliding.
So let's talk about that a little bit. Okay, so when you just have one block on a plane or wherever, you have to decide how is it going to move. If it has the potential to move in 2 directions, you have to analyze it 2 different ways. Okay? So I would watch, because the first problem I do on the video is on a problem where it can move both ways. So I would watch that video, watch the short part of that, watch that part until that problem's solved. Okay, then what Matt's talking about is if you have something and it could slide or it could tip, depending on what the loading is and where you're actually moving it. If I moved it low, I'm going to get it to slide, but if I come too high and I move it, it's going to tip. So it's quite possible that you have to analyze it for 2 things. So at the problem at the beginning of the video, had a block on an inclined plane, and the motion could have been down, or the motion could have been up. So you had to analyze it 2 ways. So the first way, with motion going up, which way would you put your frictional force?
Down.
Going down. And then you analyze it the second way, with motion going down, and the frictional force goes up. Okay, so that's one. Then, if you have another problem where there could be sliding, or tipping, you have to analyze it in two ways again and figure out which one's going to happen. So in the first one, when there's sliding, you're probably going to do some of the forces in the X and some of the forces in the Y and the friction force, and you might even do the sum of the moments. But definitely with tipping, you definitely will be doing some of the moments. So let's say it's trying to be pulled in this direction. Which way is the frictional force going?
Opposite.
The opposite. So the frictional force is parallel to the surface going in that direction. So here's my frictional force, right? And let's say that there's a rope here, right, P. And this has a certain maybe height to it. Okay? So where would you, if you did some of the moments for tipping, where would you analyze the tipping?
On the far bottom.
On this corner right here, because that's where it's going to tip, right? So let's call that point T. So I'm going to do the sum of the moments about the tipping. And then Julian, I heard you say something about what happens when you're analyzing it for tipping.
The normal is going to move to this point.
The normal, ordinarily, we have our normal here, right? For a regular problem, it's going to be in the center of it. Here's my normal. But in the case when you're analyzing for tipping, the normal actually moves to here. So when you do the sum of the moments about the tip point, there is no normal in the equation. Right. So on a regular free body diagram, we always put the normal in the middle. So when we do some of the forces in the X and Y and stuff, the normal's in the middle. But when we're analyzing for tipping, the idea is you're analyzing when tipping is, like not now, but just about to happen. And when tipping just starts to happen, this normal, the only place it's touching is over here at the point of tipping. So when you analyze it for tipping and you do some of the moments about the tip point, the normal moves here, so the normal is not in your equation. Because typically the normal is the unknown. Does everybody get that? For the regular free body diagram, the normal's in the center, but when you analyze it for tipping, your normal moves here, and when you do some of the moments about the tip, there's no normal in that equation. Okay, what are some other interesting features in friction? Julian?
Did we already go over the fact that you have to solve for both conditions?
Yeah, so in this case, when there's a problem where motion can go in two different ways, you have to solve it here, going up, with motion going up, and then you have to solve it again with motion going down. There's two solutions. Same thing with this. If there's a possibility of sliding happening and tipping, you have to solve it first for sliding, and then you have to solve it again for tipping.
Solve for what? P?
In this case, it happens to be P.
Okay.
Or maybe it might have been H.
So let's say we find two different values of P, and the question's asking
Good.
it's
So let's say we find P is equal to 100 pounds for sliding, and P is equal to 50 pounds for tipping. What do you know is going to happen?
it's going to tip.
It's going to tip first.
But that depends on the. Does that depend on the frictional
Well,
force?
it must be that H was not the unknown. In this particular problem where I'm solving for P, H must have been given to me. I knew the location of it. Yeah.
I'm working through the homework. I vaguely remember there being a maximum friction force, and then the friction force that you solve using forces
Okay,
in
so
the X and Y.
let's pull up some of the solutions. Is friction what's friction, 14?
Friction is
Number 13.
13. Okay, so let's look at the problems. So the first one is 5. Uniform ladder rests on the rough floor with coefficient against a smooth wall. Determine the horizontal force P the man exerts on the ladder in order to cause it to move. So oh, down here. This is a ladder, it says it's smooth wall, there's no friction, but there's friction on the bottom. The guy's pulling a P, so let's see how I did this. So I did the given, just like regular problems, given and find, all the unknowns. I had 4 unknowns, good, so I only had to analyze one body. So in this case, I did do both sliding and tipping. So I got a P of 17 pounds, looking at sliding.
Okay.
Then for tipping, there's no normal, right, because the normal's right here anyway. And I got a P of 15. Well, so what does that say? Does it say what's going to happen? Determine the horizontal force that the man must exert on the ladder in order to cause it to move. So that's all it's saying. So what my answer would be, in order for it to slide, I have to apply 17 pounds. But in order for it to tip, it's 15 pounds. But if the problem said, is it going to slide or tip first, what would you say?
I would say it's going to tip.
It's going to tip because it's a lower force. Let's look at the next one. 17. Drum is a weight of 100 and rests on the floor. Determine the smallest magnitude of force P that will cause impending motion. So this is a tipping or sliding problem. So go to 17. So again, I set it up the same way. I did sliding and I got a P of 136, and then I did tipping and I got 83. It means it's going to tip first. 221. Determine the maximum weight W the man can lift. Oh, this is a pulley, a good pulley problem. Determine the maximum weight the man can lift with a constant velocity using the pulley system without and then with a leading block or pulley A. The man is a leader with a coefficient of okay. So we have, let's take a look at this. So there's the weight. And what's the tension in the cables? Oh. Did I even see? Oh. All right. This will get the elbow. So we're looking at this problem here. So what's the tension in the cable? Tell me.
W, 1/3 W.
So the tension here is T. So yeah, the tension is 1/3 W in both cases, right?
Mm-hmm.
Okay, so we know what the tension is already just by knowing about cables. And now the person is pulling it at a diagonal, and here they're pulling it at a horizontal. So if you draw the person, the tension's going up here, the tension's going here, you have the frictional force and you have the normal. So scenario 1, the tension's there, and we have the normal, the weight, and the frictional force. And here, the normal, the tension is there. Unknowns, scenario 1, weight is 318. Scenario 2, weight is 360. That's kind of cool. What did we just learn? It's worth it to put another pulley in. Right? That's mechanically what we learned. So we had to use 2 scenarios just because they gave us 2 different scenarios. Okay, what's the next problem? 27. Car A has a mass of this and center of gravity. Car B exerts a horizontal force. Determine if this force is great enough to move car A. So basically, you're gonna what are you gonna analyze? It says A has a mass of something. B is exerting a force on B. So here's car A and B. A, they're given the mass of A, so you know the weight. B is exerting a force onto A, and they want to know if car A is going to move. What are you going to draw a free body diagram of?
Car A.
Car, that's the question. Coefficient of static and kinetic friction between the tires and the road. Assume, so you have a weight, you have the frictional force, because if A moves, which way is it going? If A moves, which way is it going?
To the left.
To the left, so the frictional force has got to go to the right. 27. So here's the car, here's the P coming in, the frictional force. I got a friction frictional force is equal to this. So P is 6.9 meters to cause the car to slide. Oh, and then we did it with tipping too. So P of 6.9 kilonewtons is found by doing equilibrium equations to cause this car to slide. But tipping, it would have caused a load of 22. And why is that? It's because the cars are low. If they were both Jeeps, maybe there would have been a tip.
So they had a greater height, so they.
Right, if it would have been a greater height, you would have had more of a moment created, right? But it would have had to have been both cars, right? If A was a Jeep and the car B might have just went underneath. But if both of them were high up and hitting it, it's quite possible it would have tipped because it had a higher moment. I think we have to stop. I handed out everybody grades in the class the other day, and I want you to realize that the grades reflected on here is low, because I didn't drop any quiz grades, and I hadn't put in the third exam redo yet. So who didn't get it? Gonzalo, John, Eddie, Cameron, Brandon F.